All right, good afternoon, everybody. Welcome back. I hope you had a nice weekend. We're looking today at lesson 31.01 part B, finding maxima and minima. We did the part A of this in the previous lesson, and I want to review some basic ideas that I think are very, very important. Not just in this lesson, but in calculus in general. First of all, when you're talking about a maximum point on a graph or a minimum point on a graph, whether you're talking about absolute or local, it doesn't matter. The points are referred to as maximum or minimum because the y coordinate, the function, which is the y coordinate, is a maximum or minimum. Secondly, critical points in this context are values of x that make the derivative either equal to 0 or not defined. And third, every maximum point or minimum point will correspond to an x coordinate that's critical for the first derivative. But not every critical value of x corresponds to a maximum or minimum. So to find maxima and minima, you need to find the first derivative, find the critical points of the first derivative, and then to figure out which of those critical points truly are maxima or minima, you need to do a first derivative table. All we're doing today is looking at two examples, and unlike the examples last time, some of these examples are going to lead to critical values of x that are critical because they make the derivative not defined. So the first one is y equals x cubed. Y is equal to x cubed plus 3 multiplied by x raised to the 2/3. To determine the derivative, we're just going to apply the power rule to both of those terms. dy dx will equal 3x squared plus, looks like 2x to the negative 1/3. So you should, if you need to, of course, at any point in any of these lessons, pause the video and think about things unless they're obvious to you. So I'm just moving the exponent down in front and multiplying by the old coefficient, and then I'm subtracting 1 from the exponent. Now what I need to do is factor. I've tried to teach you from the very beginning that the only useful expression in calculus is a factored one. If it's not factored, it's not very useful, typically speaking. So I have two terms. There's no common factor in terms of the coefficient. One coefficient is 3, one is 2. I can't factor anything out of that, but they do both contain x's. There's an x squared and an x to the negative 1/3. The lowest exponent is going to correspond to the greatest common factor. So I'm going to factor x to the 1/3 out, and that will leave me with 3 multiplied by x raised to some exponent. And then plus 2, because out of the second term, I'm simply factoring the x to the 1/3 out, leaving a 2. Now that exponent is an exponent that when I add it to negative 1/3, it has to take me to 2. And the reason for that is if I were to multiply these two terms together, I have to end up going back to the 3x squared. And when you multiply common bases, you add the exponents. So you're looking here for a number that when added to negative 1/3 gives you 2. Well, 2 is 6/3. So the number I have to add to negative 1 to get 6 is 7. So I have to add 7/3 to negative 1/3 to get 6/3. And we're almost done here now. All I have to do now is factor. So again, pardon me, we're done the factoring. All I have to do now is express things without negative exponents. So I have dy dx is equal to 3x to the 7/3 plus 2 divided by x to the 1/3. And now we're looking for where the derivative dy dx is equal to 0. And we're also looking at where the derivative dy dx is undefined, because those would be critical values of x. Well, the thing I want you to appreciate is dy dx is equal to 0 whenever the top of this expression is equal to 0, and dy dx is undefined wherever the bottom is equal to 0. So what we're really looking at for the critical values of x that make the derivative undefined, or the derivative equal to 0, let me start again. What we're really looking for values of x that make the derivative equal to 0 are the solutions to this equation. Where does the numerator equal 0? If we solve, on the other hand, this equation, we will be determining values of x that make the derivative undefined. So you're always factoring, writing things with positive exponents, and then solving the numerator equals 0 and the denominator equals 0. Well, let's tackle, first of all, the numerator. 3x to the 7/3 plus 2 is equal to 0. How do you go about solving an equation like this? Well, since there are only two terms and x is only contained in one term, the best advice I could give you is just start rearranging for x. We're going to have to subtract 2 from both sides to get 3x. This should be a 3 to the 7/3 equals -2. Then we can divide both sides by 3 and get x to the 7/3 equals -2/3. And now how do you go about solving this equation? Well, you want to eliminate the exponent of 7/3, and I'm going to rewrite it just so I don't crowd things together here. What I'm going to do is take x to the 7/3 equals -2/3, and I'm going to raise both sides to an exponent. And the exponent I'm going to use is 3/7. The reason why that's going to work is on the left-hand side, you have a power of a power. Just to remind you, if I had, it doesn't matter what it is, I'll use a raised to the 3 raised to the 2, that's a raised to the 6. When you have a power of a power, you multiply the exponents. And the simple fact of the matter is, when I multiply these two exponents, they're reciprocals of each other, and they're going to cancel, leaving me an exponent of 1. So I end up with, on the left side, x, and on the right side, I get this number, -2/3 raised to the 3/7. Now, we do need to, that's an exact value. And what it means is you're going to take -2/3, take the 7th root of it, and then raise it to the 3, or you can just put it in your calculator. Unfortunately, I connected a different computer to the smartboard today, and I can't get my computer calculator to work, so you can't see me doing this. But basically, I put -2/3 in brackets, and I raise it to, in brackets, 3/7, and I get approximately 0.84. You don't need to know what that number is, but I like to know what it is, and it's actually -0.84. I like to know what it is just in case I'm interested in what the graph looks like. So you get -0.84. You'll want to make sure you get the same number. It's -0.84, 0.4895, and there's other stuff. Now, when you look at the bottom of the derivative was x to the 3rd, and that equals 0. I mean, I guess if you wanted to, you could raise both sides to the 3/1. But the bottom line is the only way that x to the 3rd would be equal to 0, making the derivative undefined, is if you also had a critical number of 0. So we have two critical values of x. Now we have to construct a first derivative table. Before I actually fill in the left side of the table, let's go back up and let's ask ourselves if this function is defined everywhere. And the answer to that question is yes. The domain of this function is x is any real number. And the reason why it's any real number is when I look at the first term, which is x cubed, I can always cube any value of x. That's not a problem. When I look at the second term, 3x raised to the 2/3, what the third means in the exponent is a cube root. And you can take the cube root of any real number. You can take the cube root of negatives, the cube root of positives, or the cube root of 0. So this is defined everywhere from -infinity to infinity. And that's important because remember what I talked about in the last lesson. When you build your first derivative chart, you want to take the domain of the function and make slices to it every place there's a critical point. And by the way, this is one of the reasons why it was useful to know that this critical value of x is about negative 0.84. So we have a critical value at negative 0.84. We have a critical value at 0, which means we're going to split our domain into 3 separate pieces. It's going to be from negative infinity to negative 0.84, from negative 0.84 to 0, and from 0 to infinity. So our first derivative chart will contain the following intervals: negative infinity to, I'm just going to put negative 2/3 to the 3/7. Then we're going to have negative 2/3 to the 3/7 up to 0, and then we're going to have 0 up to infinity. And across the top, we're going to put all of the factors of the derivative. One of the factors was 3x to the 7/3 plus 2, and the other was x to the 3rd. And I know that if I were teaching this in front of a group of students right now, many of you would put up your hand because what I've written up top is not the derivative. The derivative is actually 3x to the 7/3 plus 2 divided by x to the 3rd. But the only reason we're putting the factors there is to see what the positives and negatives in the chart give us. And when you divide, the rules for positives and negatives in division is the same as the rules when you multiply. So don't forget, the quotient of these will give you dy dx because it was, in fact, a quotient. And that's going to tell us something about y. If you were involved in the Google chat last week, I think it was Spencer who asked, is there a kind of a shortcut way to do this? And what I suggested to Spencer was, when you look at a factor and you know where the 0 is, that factor will go from being negative before the 0 to positive after. I did tell him that the trick works if the factor is linear. And what I will tell you right now is the trick will work if the factor only contains 1x, if the exponent is odd, and if the coefficient of the first term is positive. So there's all kinds of things going on here. That certainly applies to the cube root of x. It will be negative whenever x is negative, and then it becomes positive. So when we divide negative by negative, we get positive for the first derivative in that interval. Positive divided by negative for the second interval will give you negative, and positive divided by positive will give you positive. Okay, so what? What does that tell us? It tells us that in the first interval, since the derivative is positive, the function is increasing. In the second interval, the derivative is negative, so the function is decreasing, and then it's increasing again. So since it's defined everywhere, there must be, at this location, a maximum. In order for the function to go from increasing to decreasing, it has to have a maximum value. And there must be a minimum here. We are certainly going to encounter cases where it might not be a max or a min because the function doesn't exist there, but this function exists everywhere. So I'm going to do the same thing I did with the last lesson. I'm simply going to make a note that there is a maximum at negative 2/3 raised to the 7/3. Geez, was that the right number? Yes, it was. No. Raised to the 3/7. The x coordinate, which is the critical point, the x coordinate of the maximum is the critical point, and the critical point is negative 2/3 raised to the 3/7. Comma, you know what, I don't really care. I think as an exercise, it would be useful for you to determine that value, but I'm going to talk about that in a second. And then there is a minimum value at 0, and you could figure out what the y coordinate is there. Again, what you would do to figure out the y coordinate is you would go back to the function which was x cubed plus 3x to the 2/3 and you could put in each of those two x coordinates to find a y coordinate. I can see right away that this y coordinate is 0. I have no idea what this second y coordinate is up here for the maximum, but you could figure it out. I would really recommend that once you have some time, you use your graphing calculator to graph this and confirm what it is we've discovered. But we're not going to spend time on the video doing that. Let's move on to the next example, which is the last one. And this one is a little bit different for a very important reason. Because it contains a radical, the thing underneath a radical is called a radicand, and a radicand can never be negative. So the bottom line is a radicand must be greater than or equal to 0 in this question. And that's going to change the domain, because you can't put in any number for x. For example, if I asked you to make a table of values, and I said, go ahead and find out the value of y when x is 20, then you would put 20 up here, and you would have 9 minus 20, which is negative, and you just can't take the square root of a negative. So we have to be mindful of that. In this particular example, 9 minus x must be greater than or equal to 0. I'm going to add x to both sides and get 9 must be greater than or equal to x, which means if we read it right to left, x must be less than or equal to 9. You cannot use a number that's not less than or equal to 9. If you use 10, it won't work. If you use 9.1, it won't work. So now let's find, this is the domain right here. Let's find the derivative. And I'm going to rewrite this with an exponent. We have y equals x multiplied by 9 minus x to the half. There is a way that you could put that x in the brackets and avoid the product rule, but I'm not going to do that. I'm going to use the product rule. The derivative of the first is 1 multiplied by the second plus the first, which is x, multiplied by the derivative of the second. So I'm moving for the second part of this, the derivative of 9 minus x to the 1/2. I move the half in front. The base remains the same. I drop 1 from the exponent, and then I multiply by the derivative of what's inside. There's two things I need to deal with here. One is the fact that I have a fraction in the numerator, and what I would prefer to do is do these two things at different places. We've talked about this in class. I'm going to multiply top and bottom by 2. We've talked about this in class that you also need to factor the numerator, but I wouldn't recommend factoring and getting rid of that fraction in one fell swoop. So when I do multiply top and bottom by 2, I end up with dy dx equals 2 times 9 minus x to the half. Then I have plus x. Well, actually it's minus. I see that -1 way at the back there. I might as well put that in front. minus x, and then I have 9 minus x raised to the negative half. So we'll just make sure, let me collect my thoughts here and make sure I've got everything. This 2 and this 2 canceled, so I'm left with negative x and 9 minus x to the half, and then I have 2 times 9 minus x to the half. I'm okay there. And this is a negative a half. And this is over 2. So now I can factor the numerator. There's a common factor of 9 minus x raised to the negative half. Remember, you factor out the lowest exponent. That leaves me with 2 times 9 minus x to the 1. When I add the exponent of 1 to the exponent I took out, which is negative a half, it gives me 1/2. And then I have minus x. This is over 2. Just about done. We have dy dx is equal to, I'm going to bring that 9 minus x to the negative half to the bottom and write it as 9 minus x to the positive half. I also have, I'm just going to clean up this set of brackets on the side. 18 minus 2x minus x, which is 18 minus 3x, which is 3 times 6 minus x. My critical values of x would be x critical equals 6 and x critical equals 9. 6 is a value of x that makes the derivative equal to 0. 9 is a value of x that makes the derivative undefined. When you build your first derivative chart, don't forget that you can only go from 9 to the left, all the way to infinity. So the domain is from negative infinity up to and including 9. That means we're going to go from negative infinity to 6, and from 6 to 9, and then we end there. We have negative infinity up to 6. Six up to 9, and that's it. We end at 9. So there's only 2 rows to this derivative chart. Across the top, we're going to put all of the factors, and I have 3 multiplied by 6 minus x, and I also have 2 multiplied by 9 minus x to the half. Now, I'm not even going to worry about the 3 and the 2. I'll put it in here, but the 3 and the 2 are positive everywhere, so they don't really play a role. 9 minus x to the half is also positive everywhere, because that means take the square root. It means specifically take the principal square root. And you're only allowed to do that if 9 minus x is already positive, so you're going to get a positive. Now, the trick that Spencer had asked me to show him during our chat is backwards here because of the negative in front of the x. And again, you're going to have to think about this stuff. dy dx would be positive and then negative. And that means that y is increasing, then decreasing. And what that means is that there must be a maximum here. So we have a maximum at 6 comma something. Now, we also have 2 other minimum. One minimum will occur at, I take that back, we have 1 other minimum, and that minimum will occur at 9. The reason there will be a minimum at 9 is up to 9 the function is decreasing, but the function ends at 9. So again, you can find the y coordinates, and I would encourage you to use your graphing calculator to graph this function. which is y equals x root 9 minus x, and confirm that at 6 comma something there will be a maximum, and where the function stops there will be a minimum. I hope you were able to follow all of that. On page 182 you can do 3A, C, and D, and 4D. For 4D, be very careful. I'm telling you the domain for 4D. So for 4D, you're going to split up your domain from -1 up to +1 only using critical values of x that lie in between those points. So you're not going to build a derivative table that extends from -infinity to infinity. If you do, then it's going to get confusing, and the reason it will be confusing is it won't work. There's a lot to take in today. It's only 2 examples, but they're pretty deep. So give some thought to what we did. Take a look at the video a second or a third time if you need to. And tomorrow, I believe, so today is Monday when you're watching this. Yes, tomorrow is Tuesday. I believe that your assignment is due tomorrow by 3:15, and I will be available in Google Chat in our chat room during period 4. So I hope that made sense, and I hope you have a great rest of the day. We'll talk to you guys later.